Imagine building like a multi-billion-dollar 100-lane superhighway for the world's most advanced AI systems.
Right, just top of the line everything.
Yeah, exactly. You pave it with the best materials, you put the absolute fastest cars on it, and then you realize traffic is just at an absolute dead stop.
Just a total parking lot.
Right. And why? Because you only built a single microscopic toll booth.
Which is just wild to think about.
It is. And today we're looking at a deeply technical source document that basically claims the entire global technology supply chain is jammed at one of these tiny, seemingly invisible bottlenecks.
Yeah.
Okay, let's unpack this, because our mission today is to decode this rapid fire, honestly, really heavily abbreviated financial thesis.
It's dense.
Very dense. But it points to a massive physical constraint in the tech world. And it's a constraint the author claims 99.9% of people are completely missing.
I mean, it is an incredibly bold claim, especially in a market where every analyst out there is just desperately searching for an edge, you know?
Right. Everyone wants the next big thing.
Exactly. And we're looking at a situation where a specific stock, it's a company called FV, that's SIVE, is being aggressively touted as the highest upside play in the market since another major player, AXTI.
Wow.
Yeah. But to really grasp why someone would make that kind of sweeping multi-million-dollar claim, we have to kind of start by diagnosing the sickness, before we look at the cure.
Makes sense. And our source text starts at the very top of the semiconductor food chain to prove this sickness is real.
Yep, it goes right to the heavyweights.
Right. It points to Broadcom, ticker symbol AVGO. And specifically, it highlights this division within Broadcom known as the Physical Layer Products Division.
Right.
So the text gives us a direct quote from an executive named Ramachandran at Broadcom. And this really serves as the smoking gun for our entire deep dive today.
It really does.
He explicitly states, quote, "Even though there are multiple suppliers in the industry today, there is definitely a supply constraint in the laser space."
What's fascinating here is the inherent tension in that one sentence.
Oh, yeah.
Yeah. I mean, think about it. Multiple suppliers, but definitely a supply constraint. You think about basic market economics. If you have, multiple suppliers churning out a component, the market naturally balances out.
Right. Supply meets demand.
Exactly.
Yeah.
Competition forces companies to scale up production. But Ramachandran is basically admitting that traditional market mechanics are just failing here.
So I guess the obvious question is why?
Right.
I mean, if the semiconductor industry is this incredibly optimized, super wealthy machine, why can't they just, I don't know, buy or build more of these lasers?
You'd think it would be that simple.
Yeah. Like, what makes them the ultimate toll booth on our data superhighway?
Well, to understand that, we have to look at the fundamental physics of how modern data centers actually operate.
Okay.
For decades, we relied on copper wires to move data, just electrons moving through metal.
Which worked fine for a long time.
It did. But as we push data faster and faster, especially now with the explosive demands of AI and hyperscale computing, copper hits a physical wall. Yeah, if you try to push a massive amount of data through copper at really high speeds, you generate massive amounts of heat.
And heat is the enemy of electronics.
Total enemy. And the signal degrades rapidly over distance, too. The physical metal literally cannot handle the traffic anymore.
Which means the entire industry is basically being forced to shift from electrons to photons.
Exactly.
We have to use light to transmit the information, which obviously requires lasers.
Precisely. And this is right where the constraint happens. You see, the semiconductor industry has spent the last 60 years perfecting the art of printing billions of microscopic transistors onto silicon wafers.
Right, they are the absolute masters of silicon.
They really are. But silicon, because of its atomic structure, what physicists call an indirect band gap, it cannot emit light.
Wait, really?
Yeah. It is physically impossible to make a laser out of standard silicon.
Wow, okay. So you have to introduce entirely different materials then.
You have to bring in exotic materials. Things like indium phosphide or gallium arsenide, just to create the laser itself.
Sounds expensive.
It is, and it's complex. Then you have to somehow perfectly align and bond that microscopic fragile laser directly onto the silicon chip.
Oh, man.
Yeah, so the supply constraint isn't just about a lack of empty factories. It's that manufacturing and aligning these optical components is incredibly difficult, highly specialized work.
So you can't just spin up a factory overnight.
Exactly. It cannot simply be mass-produced the way we stamp out traditional computer chips.
Okay, that context makes Ramachandran's warning sound so much more dire.
It's a huge bottleneck.
The traffic is backing up, the copper wires are basically melting, and building new optical toll booths requires a completely different type of engineering.
Yep.
Well, here's where it gets really interesting, because our source text zooms in on SIVE as the ultimate beneficiary of this exact physical bottleneck.
Right, they're positioned perfectly.
And the valuation jump the author highlights is honestly staggering. They say Cider went from a $140 million valuation to a $350 million valuation recently.
It is a massive leap for a hardware component supplier, no doubt.
I do have to push back a little bit on the author here, though.
Okay, let's hear it.
Is a leap from 140 million to 350 million genuinely justified by the technology? Or is this just, a product of market hype?
That's the million-dollar question. Or multi-million, I guess.
Right, because we see this all the time. A buzzword like silicon photonics or lasers hits the news, the market gets a little frothy, and suddenly everyone throws money at a small cap stock.
Oh, absolutely. The hype cycle is real.
So does the text give us actual, tangible, mechanical reasons to justify that kind of explosion in value?
The source text absolutely attempts to justify it, and it does so by detailing the specific mechanism SIVE actually provides.
Okay, what is it?
Well, it's not vaguely claiming SIVE just makes lasers. It specifically states that SIVE provides the quote-unquote CW laser light source.
Okay, the text says CW laser light source, continuous wave.
Right.
I'm imagining like a laser pointer that just stays switched on constantly.
That's actually a great way to picture it.
But wait, if the light is just a steady, continuous beam, how does that actually transmit any data?
What do you mean?
Well, information requires signals, right? Like on and off, ones and zeros. If it's not blinking, how is it communicating anything?
That is the perfect question, and it really gets to the heart of what silicon photonics actually is.
Okay.
Think of the continuous wave laser like a garden hose hooked up to a spigot that is turned on full blast.
Just water running constantly.
Exactly. The water, or in this case, the light is just flowing constantly. SIVE provides that incredibly pure, powerful, unblinking stream of light.
But it's not data yet.
Right. The actual data transmission, the blinking, happens on a completely separate silicon chip.
Oh, so another piece of hardware basically acts as the thumb over the nozzle of the hose.
Exactly that. The silicon chip acts as a modulator. It rapidly blocks and unblocks that continuous stream of light, like billions of times a second, to create those ones and zeros.
That's wild, but why do it that way?
Well, by separating the light source, the EV-CW laser, from the modulator, you solve a massive problem, which is heat.
Ah, back to the heat issue.
Yep. Lasers generate heat, and heat destroys sensitive computing chips.
Right.
So by using a continuous wave laser, you can physically locate the hot laser slightly away from the delicate processor. You just pipe the steady light in and let the silicon chip do the modulating without, melting itself.
That makes so much sense. And that explains why the text connects SIVE to some of the really heavy hitters in the tech world.
Oh, the partnerships are huge.
Yeah, it mentions a company called Jabil, ticker JBL, and specifically notes that this was formerly the Intel Silicon Photonics division.
Which is a huge pedigree to have.
Seriously. So Intel's legacy optical division is heavily involved here.
And the integrations don't stop there. The text links SIVE's continuous wave tech to Marvell, mentioning a connection to Celestial via another company, POET.
Okay, lots of names.
It lists ONET, it lists Ayar, and then explicitly notes that Ayar is backed by Nvidia and Mediatek.
Okay, having Nvidia even implicitly tied to your technology right now is basically the holy grail.
Oh, without a doubt.
I mean, they are the engine of the entire AI data center build-out.
Yeah, and when you synthesize the sheer density of those name drops in such a short snippet of text, the picture becomes very clear.
Which is what?
The tech is deeply, deeply integrated into the hyperscaler world. The massive cloud providers that run the internet infrastructure for the entire globe.
Right.
And the text points to two major technological shifts these hyperscalers are undergoing right now that absolutely require SIVE's garden hose, basically.
What's the first one?
First is what it calls future CPO scale-up.
Okay, CPO, co-packaged optics. If I'm following the logic of the heat and the distance we talked about earlier, co-packaged optics means moving the laser and the optical connections as physically close to the main processing chip as possible.
That is the ultimate goal. For years, the optical components were housed at the edge of the server rack.
Wait.
Right, so the light had to travel all the way across the board just to reach the processor.
It's like having your restaurant's kitchen in a completely different building than the dining room.
Ah, yeah, exactly.
The waiter has to literally sprint across the parking lot with the food. It takes longer, and the food gets cold.
Or in the case of data, the signal degrades and you waste massive amounts of power just trying to push it that far.
Right, right. So co-packaged optics is finally moving the kitchen directly into the dining room.
That's a brilliant analogy. And doing that successfully requires a robust external continuous wave laser to pump the light in without adding heat to that really crowded dining room.
Makes perfect sense. So what was the second shift the text points to?
The second shift is the upcoming 1.6T pluggables cycle with Jabil.
Okay, 1.6T pluggables. So optical transceivers that plug directly into the network switches to handle, what, 1.6 terabits of data per second?
Yes, which is just mind-boggling amounts of data flowing through a single connection.
That's insane.
At 1.6 terabits, traditional lasers just struggle to keep up. CZ's high-power CW lasers basically serve as the engine driving that massive throughput.
Wow.
So when you ask if that 350 million valuation is just hype, the source is fundamentally arguing that CD holds the blueprints for the exact type of toll booth required by the biggest companies on Earth to keep their data moving.
Okay, but hold on a second.
What's up?
Having the blueprints, having the most brilliant continuous wave laser design on a computer screen is great in theory.
Sure.
But if the core problem is a physical supply constraint, like that Broadcom executive admitted, you actually have to be able to manufacture these things.
And millions of them.
Millions. Which brings us away from the fancy Silicon Valley design labs and directly onto the factory floor.
We are definitely moving from the intellectual property to the physical reality now.
Right.
You can invent the perfect garden hose, but someone actually has to build the rubber and the brass fittings.
Exactly. And our source text points out a very specific hurdle regarding this physical reality.
Let's hear it.
It explicitly states, quote, with WinSemi bridge capacity scaling needed for hyperscaler supply chains.
Okay.
So WinSemi, ticker symbol is a Taiwanese stock that is a foundry.
Foundries are really the unsung heroes of the modern world.
They really are.
They're these massive, hyper-clean factories that take the brilliant designs from a company like SIVE and physically fabricate them onto microscopic wafers.
Right.
And the text emphasizes a critical phrase here, which is bridge capacity scaling.
Let's break that down, because scaling capacity in this world doesn't just mean, renting a bigger warehouse.
Oh, not at all. Earlier, we discussed how manufacturing optical components requires exotic materials like indium phosphide, right?
Yeah, totally different from standard silicon.
Exactly. So bridge capacity scaling means the foundries literally have to build entirely new hybrid assembly lines.
Wow.
They have to bridge the gap between traditional semiconductor manufacturing and this really delicate optical alignment.
That sounds incredibly difficult.
It is. They need specialized lithography machines, custom clean rooms, and just incredibly precise testing equipment. It is heavy, industrial, highly complex physical construction.
And this is where the author throws out that really aggressive metric we talked about earlier.
The 99% thing.
Yeah, they write, don't think 99.9% of people realize the sheer scale of this yet. Which loops right back to the Broadcom quote, validating the bottleneck.
It does.
But I have to actively question this metric. Are Wall Street analysts, tech investors, and people who literally track Nvidia's supply chain for a living actually missing this?
It's a fair question.
Or is it just that the physical reality of, laying concrete and calibrating lithography machines at a Taiwanese foundry is just so unglamorous that investors simply ignore it until it triggers a massive supply crisis?
This raises a really important point about how we as a society consume information about technology.
How so?
Human nature just gravitates toward the magic of the end product.
Oh, for sure.
We are endlessly fascinated by the new AI models that can generate a hyper-realistic video from a single text prompt. We love the frictionless, invisible software interface.
Right, that's what dominates the headlines.
Exactly. That is the investment narrative.
It's sleek, it's sexy, and it feels like the future. Manufacturing capacity scaling, clean room yields, and the global logistics of indium phosphide are decidedly not sexy.
Very true. The 99.9% are completely focused on the wizardry of the software.
And the rest?
The 0.1% are looking at the brick-and-mortar factories, wondering if they actually have enough physical floor space and raw materials to build the wands,
I love that analogy.
The source is arguing that the true bottleneck for our digital future isn't a lack of brilliant code. It is raw, unyielding physical manufacturing capacity.
Right.
Until Winsemi and others successfully build that bridge, the supply constraint Broadcom warned about remains an absolute reality.
So if we synthesize all of this, we've diagnosed the bottleneck, which is the industry's forced transition from copper to optical lasers.
Yep.
We've explored the technology, SIVE's continuous wave lasers acting as the garden hose for silicon photonics.
Right.
And we've looked at the massive manufacturing hurdle, the foundries needing to physically build the bridge to scale production.
We've covered the whole chain.
So how does this source material suggest a person actually navigates this ecosystem?
Well, the text concludes with an explicit, highly aggressive strategic playbook. It maps out 3 distinct lanes of investment.
And just to pause and be completely clear for you listening, we are impartially reporting the financial stance of this source document.
Yes, very important caveat.
We are not financial advisors, we do not endorse these specific trades, and we certainly aren't telling you what to do with your portfolio.
Definitely not.
Our goal is strictly to explore the logical architecture of how this author plans to exploit the bottleneck they've identified.
Right.
So having established that the whole supply chain is jammed up, what is their first lane of attack?
Lane 1 is targeting the continuous wave lasers directly. They list V, which we've dissected, and another company, MTSI.
Okay.
This is betting on these separate, high-power garden hose light sources that the new generation of co-packaged optics really require.
Got it. Betting on the specific components, solving the heat and power issues. So what is the second lane?
Lane 2 is EML lasers. For this, they list the ticker COHR, which is coherent and light.
Okay, EML, externally modulated lasers.
Right.
If CW lasers are the separate garden hose with the silicon acting as the thumb over the nozzle, what exactly is an EML?
An EML takes a totally different architectural approach. Instead of separating the light source and the modulator into 2 different chips, an EML builds the laser and the modulator directly into the exact same microscopic piece of material.
Oh, wow.
Yeah, so the thumb is permanently attached to the nozzle right at the source.
But wait, why would the industry use both?
What do you mean?
Well, if CW is the future for co-packaged optics to save heat, why is the author also pitching EMLs?
Because the tech world isn't monolithic,
Hmm.
While massive AI data centers might be shifting towards silicon photonics and CW lasers to save power, traditional telecommunications networks, like pushing data across the city, for instance, they often rely heavily on EMLs because they are highly integrated, proven, and just excellent at specific wavelengths.
Ah, okay.
If we connect this to the bigger picture, the author isn't just wildly guessing on one technology. They are acknowledging that the global laser supply constraint affects the entire optical world.
That makes a lot of sense.
By pitching both CW and EML lanes, they are betting on both architectural philosophies simultaneously.
It's actually a remarkably comprehensive approach. You don't just bet on the newest engine, you bet on the traditional engine too, because the world is suddenly desperately short on all engines.
Exactly.
And that brings us to the third lane, the text outlines.
The text says, quote, or their foundries in TS/Winsemi.
TSM, another foundry, alongside Winsemi, so they are going right back to the factory floor.
This completes the whole ecosystem play. You place your bets on the architects designing the new toll booths, the CW and EML designers.
Right.
And you simultaneously place your bets on the heavy construction companies that actually have to pour the concrete and build them.
And the source finishes this entire breathless diary entry with a provocation of its own to the reader. It simply asks, maybe it's time to wake up.
It circles right back to the 99.9% claim. The author is deeply convinced the broader market is just fast asleep at the wheel regarding the physical realities of the AI boom.
And honestly, when you walk through the mechanics of it like we just did, it is a deeply compelling narrative.
It really is.
You have an executive from a giant like Broadcom explicitly stating the problem on the record.
Yep.
You have the dense, undeniable web of partnerships linking this specific laser tech to Nvidia-backed companies and Intel's legacy divisions.
Huge names.
And you have the unavoidable truth of physics. You simply cannot software update your way out of a physical hardware shortage.
No, you can't.
You cannot code an indium phosphide laser into existence. It has to be manufactured atom by atom in a massive factory.
This entire document really forces a reckoning with how we perceive the cloud. It strips away the illusion of the digital ether and replaces it with the stark reality of supply chains, exotic materials, and manufacturing yields.
So what does this all mean? We started today with a dense, rapid-fire text full of financial shorthand and ticker symbols.
It was a lot.
It was. But when we cracked it open and looked at the mechanisms underneath, we found this fascinating detective story about the physical limits of our digital world.
We did.
We saw how pushing data to 1.6 terabits literally melts the copper wires we've relied on for decades, forcing a massive, panicked industry shift toward optical lasers.
And we saw how that single forced shift creates massive hidden ripple effects.
Right.
Suddenly, the most critical player in the AI revolution isn't necessarily the person writing the code. It might be the material scientist figuring out how to bond a continuous wave laser to a silicon chip without it overheating.
Exactly. So for you listening, the real value of this deep dive isn't just memorizing a few new ticker symbols.
No, definitely not.
It's adopting the mindset shift. It's the daily reminder to look past the flashy, intoxicating headlines of infinite AI, endless storage, and frictionless cloud computing.
Look deeper.
Seek out the unglamorous toll booths. Look for the messy physical bottlenecks, because where the physical world creates friction in the digital world, that is where the most fascinating challenges and honestly, the biggest hidden opportunities truly lie.
It is entirely about finding those specific, microscopic pressure points where the laws of physics simply refuse to be ignored by our software ambitions.
Which leaves us with one final thought to ponder as we wrap up today.
What's that?
We just spent this entire time dissecting how an incredibly advanced, multi-billion-dollar global industry can be brought to its knees by a shortage of one specific component, a tiny laser.
Right.
If our most cutting-edge, seemingly limitless digital technologies can be hard stopped by a microscopic piece of exotic crystal, well, what other invisible physical limitations are out there waiting to trip us up?
It's a scary thought.
Could the next massive bottleneck be a sudden geopolitical chokehold on the rare earth metals required for these components?
Easily.
Could it be the staggering, almost incomprehensible amount of fresh water needed to cool these new hyperscale data centers?
That's a huge issue right now.
Or could our aging power grids simply hit a hard limit, putting a sudden physical stop to our digital dreams tomorrow? Just something to think about.